Friends, welcome back to Acharya Gurukulam. Today's topic is design seismic force by static analysis method as per IS 1893 2023 draft code. In this video, I am going to explain the procedure how to calculate the lateral forces like base shear, story shear, and distribution of story shears onto frames using linear equivalent static analysis method. Before that, we would like to understand what is the earthquake design philosophy. Under minor shaking, the main members, that is the structural members which carries the load, should not be damaged. Building parts that do not carry load may sustain repairable damage. Under moderate shaking, the main members, that is structural members which carries the load, may sustain repairable damage. Under strong shaking, the main members may sustain severe damage, but building should not collapse. What is linear equivalent static analysis method? It is a simplified technique to substitute the effect of dynamic loading of an expected earthquake by a static force distributed laterally on a structure for design purpose. This method is applicable for low-rise buildings whose height is less than 15 meters and the building is located in earthquake zone 2, and it has simple configuration of structure, that is the plan of a building is like rectangular in shape, and the uniform distribution of mass and stiffness is distributed along the height of the structure. What are the various methods for determining the lateral forces? There are two methods for determining the lateral forces. One is linear equivalent static analysis method and dynamic analysis method. Under dynamic analysis method, there are two methods. One is response spectrum method, the other one is time history method. In this video, we are discussing about linear equivalent static analysis method. The Indian Standards IS 1893 code was first published in 1962 with the title Recommendations for Earthquake Resistant Design of Structures. The first revision took place in 1966, second in 1970, third in 1975, fourth in 1984. Significant time has taken to revise the codes, and also substantial revision has taken place from fifth revision onwards of IS 1893, and the code is divided into number of parts from fifth revision onwards. The IS 1893 in 2002 and 2016, the parts are divided as follows. Part 1 is for general provisions and buildings. Part 2, liquid retaining tanks, that is elevated and ground supported structures. Part 3 for bridges and retaining walls. Part 4, industrial structures including stack-like structures. Part 5, dams and embankments. And the latest revision of IS 1893 2023 draft code has further divided into 11 parts. Part 1 is for general provisions, part 2 for buildings, part 3 liquid retaining walls, part 4 bridges and retaining walls, part 5 industrial structures, part 6 base isolated buildings, part 7 pipelines, part 8 dams and embankments, part 9 coastal structures, part 10 steel towers, and part 11 for tunnels. Now we'll see how to calculate the design lateral force using equivalent uh, static analysis method. The design horizontal base shear force VBDH and design vertical base shear force VBDV along any principal direction of the building for strength design shall be estimated as VBDH is equal to AHD of T into W. Similarly, in vertical direction, VBD of V is equal to AVD of T into W, where AHD of T and AVD of T are the design horizontal and vertical acceleration coefficients, and W is the seismic weight of the structure. Here in the latest version of the code, there are two terms which are introduced. One is strength design and serviceability check. So the details of strength design and serviceability checks will be discussed with an example problem in the upcoming videos in this channel. The design horizontal acceleration coefficient along any principal direction of a building of a given structural system in a given earthquake zone and resting over a site and given a category and its design vertical acceleration coefficient for strength design shall be estimated as AHD of t is equal to AH of t divided by R. Similarly, in vertical direction, AVD of t is equal to AV of t divided by R, where AH of t and AV of t are the elastic maximum horizontal uh, pseudospectral acceleration depending on the natural period t of a building of horizontal translatory modes. And R is the elastic force reduction factor R for buildings. How to calculate the elastic maximum horizontal PSA? The elastic maximum horizontal PSA shall be estimated as AH of t is equal to Z into I into A NH of t. Similarly, in vertical direction, AV of t is equal to Z into I into A NV of t, where Z is equal to earthquake zone factor, I is equal to importance factor, and A NH of t is normalized horizontal pseudospectral acceleration. The country is divided into five number of zones: Zone 2, Zone 3, Zone 4, Zone 5, and Zone 6. In the earlier version of the code, the number of zones were Zone 2, 3, 4, and 5. And the approach was based on the deterministic in the earlier version of the code, and in the latest version of the code, the uh, uh, approach is based on the probabilistic. Here there is a tabular column which shows the zone factors for different return periods are listed for different earthquake zones. For a return period, how to calculate the return period for simple understanding. What is the return period of an earthquake that has a 2% probability of exceedance in 50 years? The probability P is equal to 1 divided by 1 minus 2%, that is 0.02 whole to the power of 1 divided by 50, that is 50 is the number of years. So after simplifying, we'll get approximately the number of years are 2475. The return period of an earthquake in 50 years period with probability of exceedance, for 2% probability, the return period is 2475 years. For 5% probability, the return period is 975 years. And for 10% probability, the return period is 475 years. The next is the importance factor. In estimating the design horizontal and vertical elastic pseudospectral acceleration of buildings of IS 1893 Part 1, the importance factor I of building shall be taken as for normal buildings for a design return period 475 years, I is ranges from 1.0 to 1.15. And for important structures, the design return period 975 years, I is equal to 1. For critical lifeline structures, design period 2475 years, I is equal to 1. For special structures, the design return period 4995 years, the importance factor I is equal to 1. For nuclear power plants and facility structures, the return period to be specified as per AERB, that is Atomic Energy Regulation Board. Next is the normalized horizontal pseudospectral acceleration, that is ANH for 5% of tapping. The plot is drawn between a natural period, that is t in terms of seconds, and design horizontal elastic pseudospectral acceleration on y-axis. Here the plot is drawn for various site classes A and B, site class C, and site class D. So these site classes are based on the weighted average shear wave velocity values. For site classification A, the upper limit is the shear wave velocity, the weighted average shear wave velocity is the upper limit is 1500 meter per second. And for site classification B, it ranges from 760 to 1500. For site classification C, the VS value ranges from 360 to 760. For site classification D, it ranges 180 to 360. And for site classification E, the value is less than 180 meter per second. For calculating ANH for 5% of damping, the values are given for different time period values and scientific classification values. Now on x-axis, we have time period. Now how to calculate the time period using IS 1893. The approximate fundamental translational natural period, that is TA, of oscillation shall be estimated by the following expressions. Here, the time for the calculation of time period for various cases, the equations are given. For bare frame, moment resisting frame buildings without masonry infills, the time period TA is equal to C into H to the power of 0.75, where C is the coefficient for RC moment resisting frame buildings. The value is 0.075. For steel, RC steel moment resisting frame buildings, the C value is 0.080. And for steel moment resisting frames, the C value is 0.085. There is a typological error here. The the value of C is equal to 0.085. Buildings with RC structural walls without and with masonry infills, the equation is given here. And for all other buildings, the time period T is equal to 0.09 H divided by root D. Next, elastic force reduction factor R, the factor by which the base shear induced in a structure, if it were to remain elastic, is reduced to obtain the design base shear. It depends on the perceived earthquake damage performance of the structure, characterized by ductile and brittle deformations, redundancy in the structure, and overstrength inherent in the design process. A schematic diagram is given here, and the plot is drawn between roof displacement and the total horizontal load. Here, the response reduction factor R is the product of the ductility mu, redundancy omega, and overstrength phi. From the diagram, it is seen that the ductility is in between F elastic to Fy, and the redundancy is Fi to Fs, and the overstrength is Fs to F design. So based on that, the formulas R is equal to F elastic divided by Fi, and omega, that is redundancy, is Fi divided by Fs, and phi is equal to Fs divided by F design. So from this equation, we can write down the response reduction factor R is equal to F elastic divided by F design. The design horizontal earthquake base shear force, that is VBDH, obtained for strength design shall not be taken less than VBDH minimum given by VBDH minimum is equal to 0.625 into ZI divided by R multiplied with W. In no case, the value of VBDH minimum shall be less than 0.015W. Calculating the design base shear. So the design base shear is distributed onto the story levels based on the equation for strength design and for serviceability check. The distribution is as follows. That is Qi is equal to Wihi square divided by sigma j is equal to 1 to n Wj Hj square multiplied with Vb. The design story shear force VI in story I for strength design and for serviceability check shall be VI is equal to sigma j is equal to 1 to n Uj. In buildings whose floors are capable of providing rigid horizontal diaphragm action on their own plane, VI can be distributed onto the various vertical structural elements in proportions to their lateral stiffness. If not, VI shall be distributed in proportion to the mass from tributary floor areas. Here, the schematic diagram is given for the design horizontal earthquake base shear force and design story lateral force and distribution of the design story lateral force on lateral force resisting elements. Here in this video, the procedure is given for calculating the design horizontal earthquake base shear to distribution of the design story lateral force on lateral force resisting elements. In the next upcoming video, we'll discuss the same with an example problem for strength design serviceability checks. Thank you, Jai Hind.